Hello, this is the fifth session in the second Matrices series of OCR Pure Core AS Further Maths. This session will look at transformations in 3 dimensions. Any of you interested in computer graphics may know that the use of matrices is widespread in programming graphics for modelling both 2-dimensional and 3-dimensional transformations using array programming languages, also known as vector or multidimensional languages. In 2 dimensions, we use 2 axes, x and y. In 3 dimensions, we have 3 perpendicular axes, usually x, y and z, where normally we try and represent this in 2D by some form of diagram where at least one of the axes in effect sort of comes out of the page. Usually Z points upwards and then X and Y, depending on the rotation, are on a different perpendicular plane. So the plane Z equals 0, for example, let me just sort of do a scribbly, would be, look a little something like that. So in this session, we're looking at transformations in 3 dimensions, but we're only going to look at simple transformations. For example, reflection in one of the planes, either the z equals 0, the xy plane, which I've tried to sketch there, or the y equals 0, which would be the xz plane, or the x equals 0, the yz plane. Other transformations we'll look at would be rotation of multiples of 90 degrees about one of the axes. Remembering, of course, that the positive direction for 3-dimensional rotation is counter or anti-clockwise when looking towards the origin from the positive side of the axis of rotation. Whereas in 2 dimensions, we quite often looked at the effect of a matrix on a unit square, or the identity matrix. Here we are going to consider a unit cube, or in effect a 3D identity matrix, to help us to identify the matrix cell elements. Just to remind you what the 3D identity matrix looked like. If you remember, we just had the ones on the diagonals, all the other cells were 0, and this is like the points 1, 0, 0, 0, 1, 0 and 0, 0, 1. And if we would like to consider this cube then, in fact if we consider that one to be the 0, 0, 0, and then this one perhaps 1, 0, 0, so that's in the x direction, and then the one, if you like, at the back there would be the 0, 1, 0, so that's this point here, and then this point here would be 0, 0, 1. So just to try and clarify where the axes are, we've got Z, we've got X, and then Y is sort of going back into the page. They're all perpendicular axes. So if we have this matrix M and we want to know what transformation it might represent, we can see by looking at it or by inspection that the y and z coordinates have not altered, but the x coordinate will change sign. So let's think about that geometrically. The x coordinate changes sign, but the y and z coordinates do not alter. This is then going to be a reflection in the yz plane. Here we can see this shown graphically. You may wish to pause here and think about things for yourselves, i.e. what reflections in the xy and xz plane would look like in matrix form. So, just to remind you, I'll write it down, that this is a reflection in the YZ plane. Alright, and you can see it's the X coordinate that's changing sign. So if you were thinking about a reflection in the XY plane, let me just write the word plane up there as well, or the XZ plane, then you might like to think about the matrix and which of those ones would be negative. If we look at a different matrix M, we again might want to pause to consider what is happening. Here, the Z coordinate is unchanged, but both the X and Y coordinates will have changed sign. You may want to pause here to consider what the 2D transformation matrix of -1, 0, 0, -1 represented. For those of you who haven't got your notes in front of you, I'll remind you that this was a rotation of 180 degrees about the origin. Hence, let us just see whether M in 3 dimensions represents a rotation about an axis rather than about an origin. If we look geometrically at the unit square and then see what -1, 0, 0, 0, -1, 0, 0, 0, 1 looks like. Okay, so C, which was for 0, 0, 1 on the Z-axis, has not changed, but the other two, in effect, you can see that A has rotated round in whichever direction, 180 degrees, to a transformed point A dash, and so has B. So in effect we can see that this is a rotation of 180 degrees about the Z axis. Given that you should be able to remember what the 2D matrix representing transformations, which were rotations of other degrees about the origin, you might like to sit and discuss what the various 3D matrices might be for rotating a different number of degrees about the Z-axis, and then move on to thinking about how you would express a rotation about the X and Y axis as well. Integral has notes for more on three-dimensional transformation matrices, and you may wish to try investigating these using the three-dimensional view in GeoGebra. If you need any help using the GeoGebra, please go to the website given below. In the final session 2.6, we will consider invariant lines and points.